Okay. So I first met Philippe. I actually didn't really meet him. I first encountered Philippe when he was visiting Tel Aviv University, I believe, maybe in '93. And I was a PhD student. I was very impressed by the work. I tried my best to follow this thing, but the main impression I got was that this is cool stuff. I want to do such things. And for many years after that, we did not overlap with activity, but I believe with interest quite a bit, because my work is combinatorial. We study quantum field theories, supersymmetric gauge theories, and we apply combinatorial techniques to study those theories. So what I will show today is an exposition of some of the stuff that we do, emphasizing the combinatorial aspect of what we are doing, and also the connection with Philippe's work. Actually, we will see that. So here's a summary of what I plan to talk about. I will talk briefly about each of those topics, just to touch upon them, to show various figures, pictures, and the first thing that we will talk about is actually the one which is connected mostly to Philippe's work, even though he will not recognize that. So let's talk about brains and Gorenstein singularities. This takes us back to '98, where that was just after high-energy theorists understood the significance of D-branes in string theory. And there was, I guess, a problem which is relatively simple to formulate. And it goes like that. The solution is actually quite an interesting solution. And that's where the work of Philippe and Jean Bernard will take place. But the formulation is like that, right? So I have a type to be superstring. It is in 9+1 dimensions. I take Dirichlet 3 branes. They occupy 3+1 space dimensions. And the remaining 6 directions I choose to be a Gorenstein singularity. And for us, a Gorenstein singularity will be, so it's a space of 3 complex dimensions. It's singular, it's conical. And we could, in order to think about that, we could just think about the orbifolds of C3 by some discrete group. So I take 3 complex dimensions and identify some of the points. So that's a simple way of thinking about Gorenstein singularity. The name itself is technical, but for us, so if we are physicists, it's sufficient to think about orbifolds of C3. Okay, so then because it's a singular space, we encounter this phenomenon that the branes start dividing. They become fractional, and the bigger the singularity is, there will be more fractional branes. And a brane has this interesting feature that gauge fields live on its world volume. So we should think about many gauge fields. And those gauge fields talk to each other, they interact. There are some strings which are connecting between the different brains. Yeah. And as a result, if I want to describe the theory which lives on the brains, I will have a quantum field theory in 3+1 dimensions, because this is where the brains live. And it involves gauge fields, matter fields, and some interactions. And because of the supersymmetry of the problem, it turns out that the best way of describing the theory is using a quiver with the superpotential. And the problem that we had was to try and compute. So the input is the Gorenstein singularity, the type of singularity. And then the output would be some quiver and a superpotential. So how do we go about doing that? So our first attempt was in 98. And we came up with such a solution which turned out to be right in case the Gorenstein singularities are orbifolds of C3. And let me give a description of what it is. So we were referring to some other brains called Neve-Schwarz brains, and there are two types of them, one which are vertical, one which are horizontal. And they divide space-time into those squares that we see over here. And then we should think about placing brains on each of these squares. So I have a collection of many brains. And there are open strings which are connecting each pair of neighboring brains. And they form such type of a quiver pattern. So you see those arrows. This thing corresponds to an open string, which goes one way, but not the other, and so on, like that. Okay? And you give them names, and you write down interactions between them, which are interactions of which take the option that several open strings can combine together and form closed strings. So if I take a string going this way, and then this way, and this way, I can form closed strings. They form an interaction, and the effective theory which characterizes this is through this superpotential term, like that. Okay? And this turned out to be a solution which is correct for the type of singularities studied back then, but not elegant enough. This was not the right description of the problem. So now, let's go back to this paper taken from Jean Bernard and Philippe. You remember that, maybe. And so this is a work from 89. I took it from the paper there. They wrote it as a graph which characterizes the orbifold singular. Sorry, actually, they were not talking about an orbifold. They were talking about a discrete group Z3 cross Z3. And if you want, this diagram here is the tensor product of a particular three-dimensional representation subgroup of where Z3 is taken to be a subgroup of SL3. And this three-dimensional representation, when I take a tensor product with all other irreducible representations of Z3 cross Z3, gives you this pattern of a product. Okay? However, this also turns out to be the answer to the question I was presenting with brains and Gorenstein singularity. They did not talk in that language, but this is precisely what I'm looking for. So let's see how it goes. So I have arrows over here. I can think of each arrow as an open string. I can think of each node as representing a fractional brain. There are 9 of them, which is the order of the discrete group. As you could count here, you could take, for example, these 9. here. And there are 27 arrows which connect those 9 nodes. Those will represent fundamental strings. And I have 18 triangles with alternating orientation. This is counterclockwise, this is clockwise, and so on. Clockwise, counterclockwise are alternating. Okay? So I wish I knew that back then. We encountered the work, we saw the work. I had some short correspondence with Jean Bernard, and I couldn't understand more at that time. So now it goes forward in time. By the way, if you have any questions, please stop me at any moment, and we can discuss that. So as I said before, the formulation was not elegant enough, so we moved to this thing that we are calling brain tilings. And actually, this was after we learned about the work of Richard Kenyon and Okonkov. They had a paper a few years earlier, describing relation between Gorenstein singularities and Castle-Line matrices. And we heard about Castle-Line matrices yesterday several times. So we call that brain tilings because that's what we were basically looking for. So here's an example of a brain tiling. That's an improvement of what we saw in the previous pictures. And so I have on the left, I have a collection of tiles. There are 6 of them, labeled 1 up to 6. I have nodes, which are the nodes of those tiles. All of those tiles are quadrilateral. I have bipartite nodes, black and white. Black connects to white and vice versa. And I could interpret this tiling as a quiver. Now, you heard, for example, in Richard's talk, you heard that quivers are representing vector spaces and maps between them. Here, for us, a quiver is just representing a Lagrangian. We use them as physicists. A node is going to be a gauge group, a unitary gauge group. So I have 6 of them. Arrow will be a collection of scalars and fermions, which are which are charged under the gauge groups that they connect. And there will be interactions which are characterized by superpotential terms, like this one over here. But in terms of the tiling, what we have 6 tiles, 6 nodes. So a tile maps to a node. An edge in the tiling maps to an arrow, and you could count 12 of them, 2 per each of those quadrilaterals. And there are 6 interaction terms, because if you take the fundamental domain of this periodic array, you will count 6 of them, and you could see that the valence of those nodes are 6 for this guy in the center, and there are 3 nodes of valence 4. One of them is depicted over here, and there are 2 nodes of valence 3, corresponding to cubic interactions. Okay, so this actually was a great success, because now I could take any tiling that I wish. I could take it to be made out of hexagons, of squares, a combination of hexagons and squares. I can take it to be double periodic, so I tile a torus, and then for each such thing I will get a quiver and a superpotential. And I can now think of it as a supersymmetric gauge theory in 3+1 dimensions. I'll compute the space of vacua of this theory. There's a moduli space of such vacua, and this moduli space of such vacua will be actually a copy of the Gorenstein singularity that is associated with this tiling. Okay, so it's a way to construct many examples like that. Any questions? How many supersymmetries do you have? 4 supercharges. So it's n equals 1 supersymmetry in 4 dimensions. And in fact, the same pictures could serve to study 3-dimensional systems with 4 supercharges, so 3D n equals to 2 and below. Right, so if I'll take one hexagon, which periodically tiles the torus, I'll get the n equals 4 theory. If I'll take n of them on a line, I'll get 8 supercharges, the n equals 2, 4 dimensions. There will be the circular quivers, if you know them. And that's the, those are the special cases with enhanced supersymmetry. And they are all nicely fitting into the structure because they are special cases of tiling. So one of them is a single tile, which is periodically tiling a 2-dimensional plane, so that's the most supersymmetric. And then the other one is periodic in one, but not in the other, so this gives you n equals 2 supersymmetry, and those which are periodic in both will be generically n equals 1. So it fits very nicely with the enhancement of supersymmetry. More questions? Okay, so this is very nice. Here's another example. This is called the conical tiling, 2 tiles, 2 types of squares. Here's the quiver, here's the superpotential. And the next point that you see, and again, this is taken from not just the work of Richard, but more generally from the work of people doing domino tilings. So they call it urban renewal, where you take one tile and you replace it by this particular pattern, and you would say that this is a renewal of some urban environment if the 4 big cities which are neighbors are just taking some space from the one in the center. However, so this turns out to be a change of the tiling. So if you try such things, you'll get very different tilings. And in terms of the Gorenstein singularity, it will give you the same Gorenstein singularity. So it's a symmetry in the supersymmetric literature. This is known as what's written over here, Seiberg duality. But this now makes the connection with cluster algebras, because if I think about this as an operation on a quiver, then it's an operation which is identified as a quiver mutation. And so that's, in fact, next time, I think there was a big break in encounters between us. I think next time we met in 2014 in a meeting on cluster algebras. And I was not sure why I was invited there, but then it turned out that it was because all of the work we did with Seiberg dualities in the context of supersymmetric gauge theories. So now we get to this connection with cluster algebras. And here's an example. So the corresponding Goldstein singularity is called C3 mod Z3. You take, again, an orbifold of C3. You identify by taking points of different phases to be the same. And if this is kind of small, the simplest possible quiver is has nodes which are labeled 1 and edges which are labeled 3. That's the general pattern. This is for the case of n1 equals to n2 equals to n3 equals to 1. And so that's the type of quiver that you see over here. And the next thing you could do is to apply a mutation, to apply a duality on each of these nodes, and you could repeat them. You'll get a pattern, and the pattern looks like this tree, the nice tree. And there is also a corresponding Markov equation, which is derived slightly different from what I've seen in the cluster algebra category, way of thinking. So in fact, this equation, the way we derive it, is to take the corresponding quiver, to think of it as a Lagrangian in 3 + 1 dimensions, n = 1 supersymmetry. There are beta function equations for the different couplings. They are known, they carry the name NSVZ beta functions. You apply them, you want to set them to 0 for reasons of scale invariance, and you set the stage like that, and what you get is this equation over here. So this is the result of demanding scale invariance. You get the whole set of solution, and here's this nice tree that you get. I found on the net another characterization of these Markov numbers, where every vertex here is a neighbor of 3 numbers. For example, this vertex is neighbor of 2, 5, and 29, and this will be a solution of the Markov equation, a result of applying dualities successively. Any questions? Okay, so there are some generalizations of that, where you take the number of nodes to be some integer multiple, alpha, beta, and gamma. You take the number of edges to be A, B, and C, and this you get some generalized Markov equation, which looks like this. And then there are some solutions. Let's not go into the details, but you get a whole pattern of such cases. And here at the this column, there is the corresponding Goldstein singularity, which is associated to those quivers. Since many of the audience are not too familiar with the geometry, I won't spend too much time on this thing, but those are some nice, mostly combinatorial games that one can perform. Okay, how are we doing on time?
Well,
2 minutes. Yeah, okay, so I prepared some. I prepared more than what I can do, so I will finish in time. So here are some nice patterns which you would get when you apply those dualities successively. Next thing in the combinatorial game is what we had with understanding Coulomb branches of 3D n = 4 supersymmetric H theories. This takes us to 2013. And now instead of quivers with arrows and superpotentials, what we have are graphs. Graphs which contain nodes and edges that connect them. And so those are the graphs which Philippe remembers from N. Jean Bernard, from the work on classification of modular invariants of SU2. And so those shows up as yet another way. They show up in so many places. They showed up in the question that Philippe had to Antoine, actually, today. So we encounter those. And now for us, we assign two geometric singularities to those quivers, which are called, one of them is called Higgs branch, and the other one is called Coulomb branch. We won't have the time to discuss precisely what they are, but what we get from this is that each quiver is representing two types of geometric singularities. The Higgs branch is the Klein singularity of type whatever it is, A, D, or E, and the Coulomb branch is the what's written over here, the closure of the minimal nilpotent orbit of the corresponding algebra. And again, I suppose that not too many people are familiar with these nilpotent orbits. A beautiful topic for anyone who likes combinatorics. I would certainly recommend. We are out of time now, right? So I'll just converge. Here I wrote some collection of details, which we definitely don't have the time to go over. There is some procedure that we are using by taking one of those graphs here. We apply to some black box, and the details are written like that. We could just scan over there, and so it involves some co-weights of the corresponding algebra. And then by the end of the day, we get a formula, which is called the monopole formula. And by this, we get a characterization of the corresponding singularity. Now, this time, because those quivers don't have any arrows associated to them, these are symplectic singularities rather than Gorenstein singularities. And there's quite some fun one can have in studying such symplectic singularities. So I will end over here. Here's the last comment, and then I will just summarize. So we have various ways of using graphs, characterizing gauge theories using graphical objects. That's the combinatorial fun. We saw once with the tiling, so you have you could get a quiver and a superpotential. We saw it once with a graph that contains nodes and edges, so those correspond to gauge groups and matter fields attached to them. And here's a third one of doing that. This is over here. So I can think of this as a Feynman diagram of a phi cube theory. You see that every node is a 3-valent node. And this particular Feynman diagram will have one external leg and a collection of n loops. And the way I assign a Lagrangian to this theory is to declare that every line corresponds to an SU2 gauge group, and every node, which is a meeting point of 3 lines, would be a matter in the tri-fundamental representation, right? It will transform. Let's say we are dealing with this node, it will transform as a fundamental of this SU2, fundamental of this SU2, and fundamental of this SU2. So now, using this dictionary, I can construct a whole set of supersymmetric gauge theories in 4D n equals to 2 now. And I have something to play. I can just look at the connection between those diagrams. Any diagram in phi cube theory, any Feynman diagram in phi cube theory will now give rise to a supersymmetric gauge theory in 4D n equals to 2. So this is the type of game that we are playing. Here's an alternative description of this, but I will not go over the details. So let me finish by saying, yeah, I think we have plenty of, actually this was showing in the talk of Antoine. He put the Affine-Grassmannian of A2, I put the Affine-Grassmannian of G2, but none of us were talking about that, so. Anyhow, so I would summarize by saying, you know, we have a collection of combinatorial tools to characterize supersymmetric gauge theories. We play some games with the graphs, we change the graphs, and then we ask how does this affect the corresponding gauge theory, and looking for the physical interpretation of such things. And since all of those combinatorial objects correspond to geometric singularities, we are also able to ask the question for the geometric interpretation of those combinatorial games, and we have a lot of fun with that. So for future of fruitful discussions, happy birthday, Philippe.
Thank you very much.
To return to the beginning of your talk on Gorenstein singularities, you showed the case of the Z3 times Z3 subgroup. Did you consider other subgroups of SU3?
Yeah, all of them. In fact, so there is a classification, and with the classification, the quivers that we would get will be just a tensor product of the particular three-dimensional representation with the irreducible representation of that particular group. They will all look the same thing, and for computation of the superpotential, so that will be an interesting question, because you did not consider that thing, even though you had it ingrained in the graph that I showed. You also had some room for the superpotential, those closed triangles, and they were very carefully set there.
Our purpose was different.
Sorry?
Our purpose was different.
That's right, that's right. So there is a translation between the language that you are using. So what I call a superpotential will be something important in the language that you are using. So there is some significance to those triangles that you had in the graph, right? So we just need to figure this out. Yeah.
You made brain tilings from dimer configurations, and you showed how Seiberg duality corresponded to urban renewal on the cluster side. But you mentioned the Castellan matrix, and did we see that appear in your work, or can you explain
Not
how
today.
it does?
So the way you do that is that given a tiling, so let's look at the so let's say over here, or maybe here. So here's a fundamental domain that you get from this particular tiling. You have two squares which wrap the torus, and now we follow the prescription of Kenyon-Okunkov, right? So you just write down, since there is one white, one black, you write a 1-by-1 matrix which depicts the way those nodes are connected. If the dimension is bigger than 1, you take the determinant. Some people like to use the permanent, but I think not in his convention, because they were putting minus signs. Richard put some effort in explaining those minus signs on edges, and then once you put those minus signs, you could just compute the determinants, and this so the adjacency matrix will be the Castle-Line matrix. The determinant will give you a Newton polygon, and there will be a significance to the numbers that you get from having various perfect matchings, if you're familiar with that. This would correspond geometrically to the projection of the some higher dimensional space, F-flat moduli space, to 3 dimensions. So there is a projection. There will be toric diagrams in higher dimensional space. They project, so you get multiplicities, and that's what the multiplicities of the Castle-Line matrix are computing.
Thank you.
Yeah.
Question two rows behind you.
So you explain us that choice of the tiling, which is choice of the graph, fixes the quiver diagram. Quiver diagram fixes the formal superpotential. The superpotential translates the peculiar features of your superconformal theory.
Yes.
My question is, what will happen if your tiling become very dense? Imagine I'm going to talk about quiver diagrams which have infinitely many nodes, infinite number of vertices. Do you expect some universal feature appear in this limit?
Yeah, so there were some ideas going around that, going under the name of deconstruction, a name borrowed from philosophy. So
no, but those, not about superconformal. We are talking about, I'm asking about superconformal theories.
So you want to, so yeah, so the ideas that I was referring to were talking about creation of an extra dimension of space-time, but you are after something different.
No, in those papers, the measure of deconstruction, it was important that you were sitting on one of those branches that you described. Because
yes.
You had to have mass scale to have 5-dimensional coupling constant finite. Now I'm talking about superconformal case. Which, from point of view of this dimension deconstruction, if you wish, will correspond to infinite coupling constant, which means the series is not defined in 5 dimensions.
Yeah, so certainly Lagrangian techniques will not be sufficient in order to get an understanding of that. You may try to use ideas from holography. And I'm not familiar with too much work which has been done about that. But that's definitely an interesting direction to take. And since we have an understanding of the general behavior of every tiling, we could definitely take a family of them, take some large and limit, and look for properties which are desirable.
Okay, I think we should continue discussions over lunch. So let's thank the speaker and indeed all the morning's speakers again.
Thank you very much.